Hello, welcome to my talk on unsteady incompressible potential flows. This is a talk on the streamline and the path-line equations. And these equations are for the streamlines and the path-lines. As we have already known, the streamline and the path-lines would be different in unsteady incompressible flows. But how different? We hardly see any examples for this. In this talk, I will target to use mathematical method to calculate the streamlines and path-lines in an unsteady flow. And the example for this talk is the linear ocean wave, which is an unsteady flow. And we will build the streamline equation and get the solution as well as the streamlines. Then we will build the path-line equation and get the solution and the path-lines. And we will see in this unsteady flow, the streamlines and the path-lines are very different. The question is an ocean wave in deep water with an amplitude A and a frequency omega. Thus, the period can be calculated as t equaling to 2 pi divided by omega. For this ocean wave, we assume the wave height, the double of the amplitude, is small when compared to the wave period. This assumption works very well for most ocean waves. The target is to find the streamlines and the path-lines in such an unsteady flow. This is a drawing of the ocean wave and the coordinate we are going to use for studying the ocean wave. For this ocean wave, the flow can be considered as a 2D flow in x and z directions. The flow would be an incompressible potential flow, and the dynamic equation and the relevant boundary conditions are all linear. As such, the wave can be mathematically solved and analyzed. For simplicity of the talk, here the velocity potential function is simply given. If you are interested in the details, you can find them in my talk on linear wave theory. The potential function phi would be given as an expression as this. Here, capital A is the amplitude of the wave, see here, and k is the wave number. It is calculated as k equaling to 2 pi divided by lambda. Lambda is the wavelength, see here. So k has the unit per meter. Omega is the wave circular frequency. It has the unit radius per second. And g is the gravitational acceleration. X is the wave traveling direction in this example. And z is the vertical coordinate. It is vertically up. And z equaling to 0 at the COM surface. Here, based on the linear wave theory, the wave elevation is given as eta as a function of x, z, and t. It is calculated as this expression. And using the potential function here, we could obtain the wave elevation as this expression. And if we draw the wave on the surface and in water, we will have some wave at this. So this is for a wave amplitude 4 meter and the wave period 8 seconds. The wave height and water depths are proportional. So this part can be taken as the amplitude of the wave, and in water that is negative. Thus the amplitude would be smaller. So at the water surface, where z equaling to 0, the wave elevation would be largest. It is given as eta 0 as this. So this is the wave we conventionally refer to. That means when we talk about the wave, we normally talk about the wave profile at the water surface other than in water, although we have waves in water. Now, from the potential function, the velocity component would be easily calculated, given as this. The velocity component on x-axis is given as the partial differentiation of the potential function with regard to x. It is given as this, and the velocity component on z direction, w, is given as this. And these are very important. We will use them to build the streamline equation and the path-line equation. Based on the reference, the book Marine Hydrodynamics, we can see the velocity vector at a certain constant would be given as this, and we can see the wave profile corresponding to the phase from 0 to 2 pi. And we can see the velocity vector would have different direction on different phase of the wave. And the velocity vector amplitude is decreased with the water depth. So at the water surface, the velocity has the largest amplitude. And in deep water, the velocity amplitude would be very small. We will use this to construct the streamline later in this talk. And for the wave, we have also the wave dispersion relation. This is the dispersion relation in deep water, omega squared equaling to gk. K is the wave number. So this relation is important, can be used to determine the wave length and some other wave parameters such as the phase velocity, group velocity of the wave, if the wave frequency is given. Now in this slide, we will use the velocity component to construct the streamline equation. And we have talked about the streamline equation in my another talk. The streamline equation would be given as this, which is corresponding to a time instant t equaling to t0, and u is the flow velocity component on x-axis and w is on z-axis. And to solve this equation, we can take t0 as a constant. It's not variable here. So we substitute the velocity component into this streamline equation. We have the expression as this. And we can take this same term away and move sine function to this side. So we have the expression as this for the streamline function. And we can easily obtain the expression as this. And integrate this equation, we have the expression as this. Here, C0 is the integral constant. And we can write this equation in a form as this and move exponent kz to the left-hand side. And the C is another constant for streamline equation. So this basically is the streamline equation. And we can obtain the streamlines by setting different C. Now we will see the first case of the streamlines taken T0 equaling to 0, and the wave elevation at 0 it is given as tan cosine kx. Here we take the amplitude of the wave 10 meter. We use this large amplitude just for the purpose of drawing, since for streamline it is independent of the wave amplitude. So we have the wave profile given as this, and based on the streamline equation, when we set different C here, we could have different streamlines. So this black dashed line is for C equaling to 0.5, and this C equaling to 0.25, and this is for C equaling to 0.1. And the red solid line is for C equaling to minus 0.25. The dashed red line is for C equaling to minus 0.1. And if we take a different instant, say T0 equaling to capital T divided by 4, that means we have a quarter wave period later for starting the streamlines. And the wave elevation would be given as this. Here you can see there is a half pi in the face of the wave. So when we draw the wave elevation, it is given as this, and the streamlines are given as this based on the streamline equation. So we can see use different C for the different streamlines. If we compare to the previous drawing, we can see when the wave to move a quarter of a period. Although the shape are same, but the phase are different if we look at the coordinate. So we can see the streamlines would be different at different instant in the unsteady flows. Now we may ask a question. Are these weird streamlines correct? Now we come back to the velocity vectors in waves as we have shown in the previous slide. These velocity vectors can be found in the reference, and it is given at a certain instant for the wave motion. As we already know by definition, on streamline, the velocity vector would be tangent to the streamline everywhere. Thus, based on this principle, we can draw the streamline for these velocity vectors. See the streamline as this, and we can see the velocity vectors are tangent to the streamline. And we can draw another streamline, and you see again the velocity vector would be tangent to the streamline. If we compare these streamlines to the streamlines from the mathematical method, we can see at the trough of the wave, here and here, we can see similar streamlines, the red line here and here, and the dashed red lines here and here. Therefore, we can see these weird streamlines from the mathematical calculation are correct. Now we move to the Path9 equation. The fluid path lines would be solved from the Path9 equation, which is defined in the Lagrangian approach, given as the expression as this. The differentiation of x with regard to t is the velocity component on x-axis u, and the differentiation of z with regard to t is the velocity component on z-axis w. And from these velocity expressions, we can obtain the expression for the Path9 equation, given as this. Now we might ask a question, can we remove the time factor in this Path9 equation as that we have done in the steady flow? The answer is no, because here in the expression of the velocity component, t here is a variable, and we cannot solve this equation as we have done in the streamline equation, because the time is a variable in the expression. Suppose we are trying to solve the equation as we have done in the steady flow. We can divide these two equations and we have the expression as this, or as this. If we substitute the velocity component into the expression as this, so we have the equation as this, or simplified to this. However, since t is a variable, and we cannot solve this equation directly in the same way as we solve the stream function. In fact, the Path9 equations are very difficult to solve, much more difficult than the streamline equation, even though this problem is quite a simple problem. To solve the problem, we can assume the wave amplitude is small, so the wave can be regarded as a linear wave. Then we can find an approximation solution to the Path9 equation, to a first-order approximation. As we have talked about, the Path9 equation are defined in Lagrangian approach, given as this. Here we can see in the velocity component, x, z, and t are all the variables. However, if the wave is a linear wave, that means we can assume the velocity particle would only differ by a small amount of an order of the wave amplitude a from the fixed point x0, z0. Then we can use Taylor series to approximate the expression of u, given as this, and these terms plus the higher order terms. And the same for the velocity component w as this. Now we can see these terms would be in an order of a squared, because x minus x0 would be an order of a. The same for z minus z0 has an order of a. And the partial differentiation of the velocity component with regard to x and with regard to z are in an order of a. So time this together will make these terms in an order of a squared. So for the first order approximation, we can drop all these terms to simplify the problem. Hence, for a first order approximation, we have the expression for the path 9 equation as this. Now here x0, z0 are constant, not the variable. Thus the expression this and this are only time dependent. This would be different from the full expression of the path 9 equation. And in here, x and z are the variables. For the approximation equation, we can easily integrate this equation, so we obtain the expression as x minus x0 given as this, and z minus z0 given as this. So we can make a trajectory of the fluid motion given as this, and we can see the fluid particle motion would be in circles. Suppose we have a wave profile given as this, and for the path 9 equation, the first order approximation, we can draw the path 9s for different x0, z0. Now we can put the streamlines and the path 9s together. This is the wave profile, and these are the streamlines based on the streamline equation given as this, and each streamline corresponds a different constant c. And for the path 9s, the path 9 equation given as this. So we can draw the path 9s for different fixed point x0 and z0. So we have different path 9s. So we can see in the unsteady flow, the path 9s, the circles, are very different from the streamlines, the catenary lake lines. Thus, we can mathematically show the difference between the path 9 and streamlines in the unsteady flow.